Hey, we want to talk about polar coordinates. We're going to think of polar coordinates as an alternate map to two-dimensional space, an alternate way of identifying all the points in two-dimensional space. The coordinates that we have so far, where we list X and Y, horizontal and vertical components, are rectangular or Cartesian coordinates. So rectangular coordinates are also Cartesian coordinates. Cartesian for René Descartes, who was credited with the idea, which historically means he most certainly did not come up with the idea, but that's only because it's named after him. It's probably not him. Pretty much like anything Edison ever did, someone else did it. Edison either just stole it and marketed it that way, patented it really, or stole it, modified it just a little bit, and then patented it. Like if you want to post like copyrighted material on YouTube, you change it a little bit. I don't know, see, it's different. Dum 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 dum. See, it's different. So Cartesian coordinates or rectangular coordinates. We're just listing how far this point is horizontally from the origin and how far is it vertically from the origin. Rectangular coordinates that we all know and love, X and Y components, coordinates. Polar coordinates do things differently. Polar coordinates only have one distance. Polar coordinates say how far is that point from the origin. And then we say if we make that terminal, if we make that side from the origin to that point, the terminal side of an angle, and where the initial side is the positive x-axis, how far do we have to turn? So here we have polar coordinates. These will produce some very different looking graph paper. Because instead of a bunch of horizontal and vertical lines that are all perpendicular and parallel lines, we'll have a bunch of concentric circles for all the different distances we can do from the origin. And then we'll have a bunch of angles going around. So think about what the graph paper would look like for polar coordinates versus rectangular coordinates. Now, we're still describing the same two-dimensional space. We're just putting a different set of graph paper on it. Instead of a grid, we're going to put a bunch of circles. So we should be able to take any address that we have in rectangular coordinates and change that to an address in polar coordinates. Conveniently, if instead of putting y over here, next to the axis. So I put y over here. We can see exactly how this is going to go. Because if this point is at x and y, that means x is this distance down here, and y is this distance up here, this vertical distance. If the coordinates here are r and theta, then r is going to go on the hypotenuse, and theta will be this acute angle. I'm drawing it as an acute angle here. Now we know how all these coordinates are related. We could say that the sine of theta is opposite over hypotenuse. If I multiply both sides by r, now tell me that y is r times the sine of theta. Cosine of theta is adjacent over hypotenuse. If I multiply both sides by r, then x is equal to r cosine theta. So if I have r and theta, I can calculate what my x and y coordinates are. I can also write r and theta in terms of x and y. Here we put x and y and wrote them in terms of r and theta. We can also write r and theta in terms of x and y. So if we want a relationship between x, y, and r, since we're looking at a right triangle, we can say x squared plus y squared is equal to r squared. So r is going to be the square root of x squared plus y squared. There's r in terms of x and y. If I want a relationship between theta, x, and y, notice that y is opposite theta and x is adjacent to theta. So going back to the very beginning, that means we should use tangent, because tangent of theta is opposite over adjacent. So we might write theta as tangent inverse of y over x. There's more to it than just tangent inverse of y over x. You've got to worry about what quadrant we're in. We know that tangent inverse will only return values in the first and the fourth quadrant. So we got to be careful about that. Let's suppose we have a point with rectangular coordinates of 3, -4. So 3, -4. And we want to locate this point in polar coordinates. So that point is 5 units away from the origin. Now I have to figure out what angle we make with the positive x-axis. So now I can do a tangent inverse. So tangent of theta. The thing that we're going to have to remember is that we're going to get a reference angle. No, we're not going to get a reference angle. This is going to come out negative. I have to decide how we want to think about this. Oh, well, let's just do it this way. Let's just do it the way I originally started. You just drop in tangent inverse of y over x. We got -4/3. And I want tangent inverse. Here's an angle that's definitely in the fourth quadrant. So I could say that this angle is -53.1 degrees. Fourth quadrant is in the range of the inverse tangent. So I'll have to mess with anything here. But the coordinates here we could write as 5 and -53.1 degrees. The interesting thing about polar coordinates is that because one of the coordinate is an angle, we have an infinite number of ways to represent that angle. Only a few that are going to make sense, but technically an infinite number of ways. Because if instead of going -53.1 degrees for the positive x-axis, if I go around one full circle and add 360 degrees to this, it's also at 306.9 degrees. In terms of degrees, these would be the only two that really made any sense. We could go another 360 after that and say that this is 600 and, I can't add. Oh, then it's 666.9. So we say. But that would be a weird way to describe what's going on. That would be like referring to numbers like, I don't know, 20 -3 instead of just saying 17. Any questions? We do got to watch out for quadrant stuff. Let's say we have rectangular coordinates of -3, 4. R doesn't care because R has stuff squared in it. So R is still going to be the square roots of -3 squared plus 4 squared. So that's still going to be fine. But we got to figure out where that 53-degree angle is going to show up. So that is still 5, no question about that. That's all. We're all good there. But then if I just drop these into theta, tangent inverse of opposite over adjacent. We still get -53.1 degrees. And it's not the same -53.1 degrees that we had in the previous problem. This is because we've jumped over into the second quadrant. Tangent is negative in the second quadrant, but that 53.1 degrees, that's not in standard position. But angles like this are always measured from the x-axis. This one is just measured from the negative x-axis. It's going to be the negative x-axis because from the negative x-axis because we're in quadrant 2. So we got to figure out where that is. It's 53.1 degrees before 180. So the theta that we can use is 180 minus 53.1 degrees. Or 126.9. So we would list that point, the coordinates there as 5 and 126.9. We can also go around the other way. If I subtract 360 from this, another location, another set of coordinates for this same point could be at 5, negative 233.1. So beware that your angles land in the proper quadrant because we have our 0 angle is the positive x-axis. So we're in the second and third quadrant. We're gonna have to worry about measuring from the negative x-axis. Any questions? Oh, there's no point in doing that. Oh, I'll just take it. I don't remember the angles. So suppose we have polar coordinates of 13 and 215 degrees. So it's going to be in the third quadrant. So 90, 180, 270, so 215 is going to be somewhere in here. Here's where the 215 would go. And we would be 13 units away. And we want to figure out the X and Y coordinates of that point. So the coordinates in polar coordinates, I would just say 13, 215 degrees. So I just do r cosine of theta, and we get negative 10.6. And then for y, we'll get r sine theta. So 13 times the sine of 215. Negative 7.46. Rectangular coordinates are not going to have multiple representations. We get the multiple representation for polar coordinates because one of the measurements is an angle. So if instead of 215, I measured this as a negative angle, so 360 minus 215, or better, I should say 215 minus 360. And I mark that angle as negative 145. So if instead of calling this 215, I said this is the point 13, negative 145. If I grab my calculator and ask for 13 times the cosine of negative 145, I still get negative 10.6. And y is still r times the sine of theta, which is 13 times the sine of negative 145, which is still negative 7.46. Any questions? How's everyone okay? We still have an axis, but in this case, the axis, we still have an origin, but in this case, the origin is acting as a pole rather than just a point. So we're spinning around the pole. Questions? Comments? Here we have a completely new way of describing every point in two-dimensional space. And it was still just based on stuff that we already had from the beginning of class, solving right triangles. Here, the right triangle that we'd be looking at The angle would just be a reference angle for 215 degrees. Good question. How's everybody, okay? We do have to agree on what our origin is going to be and where the positive x-axis is going to be. That has to be standardized. But that's just with any coordinate system. With any coordinate system, we have to say, where's 0, 0 going to be? Even though we generally view a map as a plane, there are other places, even other places nearby, where we have the same address, same coordinates. So to keep things simple, so we don't have to have the origin of all addresses be like the center of the United States, we just have a number and a street to give you a horizontal and vertical components. And then we have to have a third one, even though it's a two-dimensional thing, we have to give a third one, a zip code, just to describe points on a two-dimensional plane. That's how inefficient this system is. We describe points on a plane with 3 coordinates: house number, street, zip code. Questions? It's funny that with the zip codes, we still write city and state as part of the address. It's actually really annoying because we have a completely different city called South San Francisco. And apparently there are some addresses that are in San Francisco and also in South San Francisco. And even though you write down South San Francisco 94080, they say, oh, I'm going to shorten that because that takes up too much space. And I'll just say San Francisco. And then the computer's like, oh, that's not the zip code for San Francisco. Use this zip code instead. And then all my shit suddenly gets sent to South San Francisco. It was the other way around. All this shit is getting sent into San Francisco rather than South San Francisco. And I got to call them up and say, where's my shit? And I go, we sent it to this address. Michael, did you leave the South off? Yeah, because it took up too much space. And did you therefore change the damn zip code? Well, yeah, because that didn't match. And you didn't think there might be a reason that those two don't match? No, you owe us a late fee. So I moved to San Bruno. And my address in San Bruno also exists in South San Francisco. I know this because I ordered some stuff and I go, where's my shit? And then I call them up, send me the shit. And then like a couple weeks later, this very nice lady that lives at my address in South San Francisco shows up at my door. I think you got these. You might want to have a word with them. Like, well, you brought these all the way over from South San Francisco? It's, well, it's just like right over there. And it was really cool. And I got to return the favor later on. So I got some of her mail. I'm like, well, yes, I get to return the favor. And also now I know your name. So I was able to look at that. Anyway, what are we talking about? Oh, this is because we're using 3 numbers to locate a place on a 2-dimensional plane. You know what I mean? Anyway, maybe our address should just be GPS coordinates, because then we just need 2 of them. until we destroy the atmosphere on the surface of the Earth and have to bury ourselves underground. Because then we'll need three. We'll need coordinates and then how deep underground we are, right? Incidentally, that's one way of doing things. We can describe three-dimensional space either with three distances like X, Y, and Z, or two distances and one angle, R, theta, and Z, or one distance and two angles. It becomes rho, theta, and phi. We can't do three angles because then we don't know how far away things are. So the reason GPS coordinates work is because, well, here's the latitude and longitude. Both of those are angles. So we just figured that that's a point on the surface of the Earth. So if we want to describe where a plane is, we'll have our coordinates plus an altitude, a distance above the surface, rather than the distance from the center of the Earth where the plane is, because that would be like really unnecessary. You know what I mean? Plus, it could just be coordinates, and then the address could be just attached to my phone in my pocket. Something like walking down the street, order a pizza, and the flying drone will just deliver a pizza to us. So I'll have pizza and walk over. Maybe that's not such good. Any questions? Not about delivering pizzas. That only came up because I skipped lunch, I think. That's right. When all you can tell that I skipped lunch because all the examples will be food, whether it makes sense or not. So you're right. I'm talking about apparently I want to 3D print myself a pizza. All right, that's going to do it for today. We will think about describing things in polar coordinates. And then we're going to completely change this into something new that's just not new at all because it's math and there's nothing ever new. That's it for today. I'll see you all on Thursday. We're going to have a good couple of days, and thanks for playing.